Hello, can you hear me?
We hear you.
So I will start then.
Please do.
Thomas, Maxim, thank you very much for the opportunity to give this talk, and also thank you very much for giving all us a sweet illusion that everything goes as usual, that we can meet, we can give talks, we can discuss things. So thank you for that. And I will be talking about a piece of work which we did with my friend and collaborator Raffaele Barelli from the University of Turin. And I moved to China 4 months ago, and now I work in Hangzhou Jiangxi University, which means Electrical Engineering University. And since I need to get my Chinese name, here is a short line of approximations how to get from my original name to my Chinese name. And I will be talking about a new method, which we called thermal Schrödinger equation. So it's a combination of Thermofield dynamics and for formulations of the problem and matrix product states or tensor train methods for the solution of the necessary dynamical equations. And this is a method which allows to calculate quantum dynamics and femtosecond spectroscopic signals of systems with many electronic and vibrational degrees of freedom, fully quantum dynamics. But before I go into details of the method, I just want to put it into some context. So what I want to say is that I have a feeling that we live now through the computer revolution in theoretical spectroscopy or in computational spectroscopy. So if you look at Schaul's book, you will see the mostly fundamentals, things and models. But nowadays, due to the advent of computers and quantum chemistry packages, so we can do a lot of things ab initio. So we can parameterize our Hamiltonians by using true molecular parameters. We therefore can use more complex and more realistic models for the simulations of dynamics and spectroscopic signals of our systems. And of course, the golden dream of probably the entire community is to move on the fly, to do all dynamical and spectroscopic calculations on the fly. But as far as I can see, there is a certain way to go to fulfill this dream, because it's really very hard to do quantum dynamics of many bodies of systems with many degrees of freedom on the fly without resorting to various approximations. And that is why in this talk, I will be using the middle way, so to say. So just how to use realistic ab initio justified Hamiltonians for the to which we can include many relevant vibrational degrees of freedom, and how we can fully quantum dynamically do the simulations and calculations. And of course, there exist many very well established approaches. If we speak about dissipative dynamics, and then the most powerful approach is, of course, HUM. And HUM was applied many times to the simulation of various spectroscopic signals. If we consider Hamiltonian dynamics, then probably MCDDH is the most powerful and the most popular approach. But quite surprisingly, MCDDH wasn't applied so frequently to the evaluation of spectroscopic signals. People just prefer to calculate quantum dynamics. And of course, there are various Gaussian basis sets methods, like Gaussian MCDDH, Davidov-Ansatz methods, multi-configurational Ehrenfest, and other methods. And what I will be talking about is this Thermofield dynamics tensor train approach. This is a method which allows calculation of quantum dynamics and the simulation of spectroscopic signals of systems with many degrees of freedom, fully quantum mechanically, and at final temperature. And just as a side remark, so before, people invented a lot of beautiful methods which were considered really like analytical methods, for example, memory functions, projection operators, and thermofield dynamics belongs to this realm. So it was just invented as a nice tool to bring temperature to the Schrödinger description, and people just played with these and for some simplified systems. But now, many of these methods are developed into powerful numerical tools, and I hope I will be able to show you and to convince you that this thermofield approach can also be turned into a powerful numerical tool for the simulation of signals and quantum dynamics. And as I mentioned, so the thermofield framework allows us just to incorporate temperature into the Schrödinger equation, into the wave function description of the system dynamics, driven system dynamics. In other words, it allows exact mapping. I emphasize that the mapping is exact, no approximations. So it allows reformulation of Liouville von Neumann quantum equation at finite temperature into the corresponding Schrödinger equation with explicitly temperature dependent Hamiltonian. And I'm not going to show you mathematical details of this procedure. It's quite beautiful and nice. I just want to share with you the structure of the corresponding Hamiltonians. And for that matter, we will consider the standard or original, let's say, excitonic Hamiltonian, or if we think about molecular aggregates, or linear vibronic coupling Hamiltonian, if we think about polyatomic chromophores. So what we have a bunch of electronic states, possibly with couplings, and we have a certain number of vibrational modes. And these vibrational modes are coupled to electronic states. And these G, K, N are just electron vibrational couplings. And if we reformulate the problem in terms of this thermofield dynamics approach, so what we will get this Hamiltonian. And when you look at this Hamiltonian, you will see that electronic or excitonic part remains absolutely the same as in the original Hamiltonian. As for vibrational degrees of freedom, so we will see that the number of vibrational modes doubles in comparison with the original excitonic or linear vibronic coupling Hamiltonian given above here. So we have the original physical vibrational modes, which are denoted by these AK, creation annihilation operators. But on the top of it, we have also so-called additional or tiled modes, which are just copies of these original physical modes. So they have the same vibrational frequencies. And as for electron or exciton vibrational coupling, so you see that it is modified. So if the original coupling was GKN, you see that the original physical modes are coupled to the electronic states by this GKN times temperature dependent factor, this hyperbolic cosine. And our additional tiled modes, they are also coupled to the electronic states, but the coupling is determined by this hyperbolic sine function. They're just determined through the vibrational frequencies of our modes. And you see that if temperature goes to 0, these guys will give 0 and disappear, and these will give us 1, and we come back to the original excitonic Hamiltonian. If, however, we have a finite temperature, then these fictitious modes are responsible for this temperature effect. And the higher is temperature, the stronger is contribution of these fictitious modes to the dynamics. And what I want to emphasize that this is just Hamiltonian which can be used as a normal Hamiltonian, like these Hamiltonians. No approximations whatever. So all observables, all possible observables can be calculated with these new Hamiltonian by using standard, absolutely standard expressions of the Schrödinger dynamics. And in principle, that is why this approach can be applied, Thermofield dynamics, to the problems we are interested here in 2 ways. First way is just if you have a smart idea how to use your original Hamiltonian at 0 temperature, then you can apply absolutely the same idea to this Thermofield Hamiltonian, because it just parametrically depends on temperature and its structure is absolutely the same. So we can just get Horn-Kreis factors depending on temperature, and you can try to do semi-classical dynamics with explicit temperature dependence and so on and so forth. And the second way to apply it is just to use it as an efficient numerical tool. You can just try to harness it into any wave function based quantum dynamics method. For example, you can just incorporate it into MCDDH and do dynamics with this Hamiltonian to take into account temperature. But what we did here, with Rafael, we used tensor train, so matrix product state approach. So the idea is just to split multi-dimensional objects which govern quantum dynamics with many degrees of freedom in straightforward basis set representation just to give a smarter way to represent this multidimensional tensor. And the very rough idea about how it works is that if you have n-dimensional tensor, in the limited case, you can just describe it as a direct product of, let's say, d vectors. But of course, this is in the case when all components are, let's say, independent. But in general case, if you have this n to the power d object, d-dimensional tensor, you can just try to represent it not as a direct product state, but as just a matrix product state. And you can just start from purely diagonal matrices, then it will be corresponding to the direct product, and then gradually increase the dimension of the matrix. And if you find a clever balance, then the dimension of this product state will be much, much, much smaller than the original dimension of this object, which you would get by using just a standard basis set representation. And here is the gain which you get. So instead of this exponential scaling, you have much, much milder scaling of with the dimension of your problem. And you can formulate it in the time domain. You can just use this method for integration of the dynamical equations by different means. We used these projection operator techniques, and we used the software developed by these guys. And in the remainder of my talk, I will try to show you that this really works, and this is quite powerful. And as just to demonstrate how it works, we considered FMOR. So we took 7 electronic states, and for each bacterial chlorophyll, we took 74 vibrational modes with ab initio spectral density. So all in all, we had 7 electronic degrees of freedom and more than 500 vibrational modes. And as I explained that in this Thermofield dynamics method, the number of vibrations doubles. So all in all, we had double of that number, so more than 1,000 vibrational modes. And to describe these dynamics, you can just introduce spectral densities for original vibrational modes and for these additional or tiled vibrational modes. And if this is just the standard original spectral density, so you can introduce these spectral density, temperature-dependent spectral densities, which are re-normalized by these temperature-dependent coefficients. And you see that at relatively small temperatures, contribution of these additional tiled modes is relatively small because these hyperbolic signs are relatively small. But if you increase temperature, the contribution of these modes, which are indeed responsible for the temperature effect in your system, increases. And in the high temperature limit, of course, they will contribute on equal footing into the dynamics. And these are just simulations or just illustrative simulation for populations, just assuming that everything seeds in the beginning in site 1. So, and you see that temperature effects are quite considerable in these, let's say, ab initio justified multi-dimensional model. You still see at room temperature certain oscillations, and these oscillations in population persist at quite long times. So temperature doesn't completely kill these oscillatory behavior of populations. And what is important that this method can also be applied to the calculation of nonlinear response functions. And this is just a cartoon expression for the nonlinear response, third-order response functions. And basically what you need to know just this propagator with this Thermofield dynamics Hamiltonian acting on the ground state of your system. So if you know these, and if you know this function, which is defined as psi of t, so you can just calculate this bracket expression, and the operator in the beginning is just propagating the electronic ground state. And for this model, it's given for free because it's described just a bunch of non-interacting harmonic oscillators. So first you pre-calculate these, and once you do that, you can calculate all necessary response functions. And for illustrations how it works, we just again used FMO, but now we just simplified the problem a little bit. So we just considered 2 vibrational states per chlorophyll with these low frequency modes, which were detected in many recent experiments on FMO. And so from a purely technical point of view, this calculation is simpler than the calculation I just showed you before. But of course, with this model, we were able to calculate all these response functions for this multi-dimensional 28-mode problem. And when we were thinking about what to calculate, which signal to calculate, we decided to calculate time and frequency resolved fluorescence of FMO. So a lot of people simulated 2D and pump prop signals of FMO. But to our knowledge, nobody tried to calculate this time and frequency resolved fluorescence of FMO, and nobody tried to detect time and frequency resolved fluorescence of FMO. People detected, but on the nanosecond time scale. But what I'm talking about here is just femtosecond time and frequency resolved fluorescence. People, of course, did calculations of these signals for other molecular aggregates, but it seems that somehow FMO escaped probing by this time and frequency resolved fluorescence technique. And here are just 2D views of these signals. So this is time, this is frequency, and the signals are calculated for 4 different time resolutions. So this is ideal, which would be detected with perfect time and frequency resolution. But since time and frequency resolution in fluorescence are Fourier limited, so you cannot get in reality simultaneously good time and frequency resolution. So that is why we use this took time frequency resolution into account and simulated the signals for time resolution of 20 femtoseconds. So the meaning is that time resolution of fluorescence up conversion setup is 20 femtoseconds, 50 and 100. So probably this is too optimistic for true experiments, and this is quite reasonable time resolution which can be obtained in this technique. And the left panels are just simulations of these signals without static disorder. So just we take standard parameters for the excitonic Hamiltonian and calculate the signals. And these signals are with static disorder. So we just assume that excitonic energies have static disorder with 100 inverse centimeters dispersion. And when you compare these signals with Z signals, probably it's difficult to say something definite about what is the difference. Definitely there is some difference, and definitely you can see that time resolution, of course, and frequency resolution affects the signals. And maybe you can say that these signals on the right panels, which are calculated with static disorder, are more regular. So oscillations, which you can see here, are more regular than oscillations here, for example. But to get a better view and better understanding of what is going on, let's have a look at the cuts of these spectra, which are just plotted here. Again, no static disorder. Here with static disorder. Again, these different time resolutions, and just cuts are taken at representative frequencies at which the signal is essentially non-zero. And when you have a look at the cuts calculated without disorder, so you see that, of course, there are nice oscillations, not even oscillations, but in the true sense of the word. So the signals are non-monotonic, they go up and down, but it's difficult to pin down these oscillations to a certain frequency. And it's not surprising because all these oscillations are caused by vibronic effects. So by this, since we have quite a strong exciton-vibrational coupling in the excited excitonic states, and this fluorescence gives us information exactly, precisely about the wave packet motion in the excited excitonic states. So it's governed by the excitonic frequencies, and that is why definitely we see these excitonic effects and excitonic oscillations, but the dynamic is a bit irregular. So we cannot just deduce a certain period, cannot assign a certain period to these oscillations. But if we consider the situation with the static disorder, the situation is different. So let us consider, for example, this signal, which is evaluated for 20 femtosecond resolution. So you see that after a certain initial time, the oscillations correspond exactly to vibrational frequency. And so I just remind you that we have two vibrational frequencies, and the oscillations correspond to the second overtone of this omega 2. So the oscillations are twice faster than oscillations which are caused by this original vibrational frequency. And of course, if the time resolution is increasing, you see quite irregular oscillatory behavior. And the reason is, of course, simple, because in that case, the time resolution is just comparable to the period of these beatings and vibrational beatings. And you cannot see this irregular vibrational oscillation. But of course, you can see some oscillations which are the result of these true vibrational oscillations and limited time resolution. But now the question is, what is the reason of these vibrational oscillations? So I just remind that these oscillations are in the excited electronic state. So it is people detected and simulated many times oscillations coming from the excitonic ground state, when dynamics is purely vibrational, and it is clear that oscillations will also be purely vibrational. But here the situation is different. We are sitting in the excited excitonic manifold. And there are two reasons, basically. One reason is that if we consider the molecular aggregates consisting of, let's say, n chromophores, then you can introduce the totally symmetric mode, which corresponds to, basically, which is a sum of all vibrational modes of the chromophore divided by the square root, one of the square root of the number of chromophores, and the same for momentum. And if you do simple math, you will see that this Hamiltonian, which corresponds to the totally symmetric mode, just decouples from the exciton-vibrational dynamics. So it just behaves like a shifted harmonic oscillator with these electron vibrational couplings renormalized by the number of electronic states in your molecule. But since for chlorophylls, reorganization energy is small, exciton vibrational couplings are small, and these purely symmetric, let's say, fictitious chromophore, which is decoupled from the entire dynamics, has even smaller exciton vibrational coupling. This is not the main reason for the vibrational oscillations we observe in these simulations. And the reason is this static disorder-induced melting of vibronic eigenvalues of our system. And the reason is, of course, that if you have exciton vibrational system and you have excitonic couplings, and all your vibronic systems depend on excitonic energies, of course, inter and excitonic couplings. But if you have static disorder, you just average your signal over different values of the electronic energies, which means that your excitonic eigenstates, multidimensional, of course, eigenstates will change due to this static disorder. But if you do averaging, you can show that this change of the excitonic eigenvalues do not produce completely chaotic behavior, let's say, of the remaining dynamics. So what I'm trying to say is that the vibrational frequencies, which are not subject to static disorder, will contribute to dynamics in the more regular way, and they will manifest themselves in the dynamics or in the spectroscopic signal. And you can just show more or less quasi-analytically that if you do orientational, if you do this static disorder averaging, then by using stationary phase approximation for evaluation integrals, you can show that at a time which exceeds a certain specific time, characteristic time, 1 over characteristic value of static disorder, dynamics will be roughly purely vibrational. So the main contributions will be just from vibrational dynamics, and leftovers of vibronic dynamics will see it in these coefficients A and phi, which are slightly determined on, which are slow functions of time. And this is the reason why this excitonic averaging doesn't kill this oscillatory motion completely. So what remains, at least here in this model of FMO, is purely more or less vibrational dynamics, which is induced by the melting of excitonic eigen or exciton vibrational vibronic eigenvalues of the original system. And so let me stop here. these are the brief conclusions. I try to convince you that this method, which is based on Thermofield dynamics and tensor trains, is quite powerful. It can allow us to treat really multidimensional systems and not only calculate dynamics of these systems, but also simulate spectroscopic signals of this signal for these signals systems. And if we talk about FMO or about vibronic dynamics in the excited state, so it seems that there is room for purely vibrational dynamics, not only in the excitonic ground state, but also in the excitonic excited state, due to this melting of these electron vibrational eigenstates of the multidimensional system due to static disorder. So this melting doesn't kill everything. So, and what remains is predominantly vibrational contributions, which show up in spectroscopic signals and hopefully can be detected experimentally. So let me stop here. Thank you very much for your attention.
Thank you very much, Maxim. So there's time for questions. So as I said before, you can just raise your hand and there's a question from the panelist. There he is.
Shall I stop sharing the screen? Or?
You can keep sharing. Darius will ask his question, I think.
Hi, Maxim. Thank you. Very nice talk. I have a fundamental problem with understanding actually Thermofield dynamics, and I hope you can clarify this. My problem is the following. Now, you introduce some additional degrees of freedom, so you get temperature-dependent couplings, and then you end up in a new Hamiltonian. So yes. My problem is that when you end up with Hamiltonian, I mean, later I want to make some calculation with that Hamiltonian, and the Hamiltonian conserves energy, so I would expect no relaxation. And then in principle, I can calculate the dynamics at an arbitrary temperature with the current Hamiltonian. So, I mean, I get like two temperatures, one temperature as a parameter in Hamiltonian, and then another whatever temperature I want to use this Hamiltonian for. So basically, how does this temperature translates into calculations? Because, I mean, I can set Thermofield temperature to 0, for instance, and then I can calculate at whatever other temperature. So this, I don't understand this. Could you clarify?
I will try. So, I mean, first of all, please do not do double counting of temperatures. So if you introduce your temperature into this Thermofield Hamiltonian, then no need to consider other temperature. No need to use this Hamiltonian for in the Liouville equation, for example, for calculation temperature. So this Hamiltonian contains already temperature, and it looks like a Hamiltonian. I mean, this Schrödinger equation looks like a standard Schrödinger equation at 0 temperature. So you should just use this Hamiltonian as you would use it in the standard Schrödinger equation. But what is important here is that you introduce these additional degrees of freedom, additional vibrations, but they are fictitious in a sense that they are not physical. And when you calculate any observable, any expectation value, you should calculate expectation value of your physical variable, for example, of your physical energy, of your physical vibrational energy. And due to the fact that this extended Hamiltonian, and I mean, for your physical system is just subsystem of this extended Hamiltonian. So that is why you will have all these temperature effects correctly. So I think the total physical plus fictitious energy is conserved, but for the physical subpart, you have an energy exchange between these physical degrees of freedom and fictitious degrees of freedom. And that is why you can describe this temperature effect correctly and exactly. And it is very close to Liouville equation, of course. But a nice thing about that is that in Liouville equation, you double all excitonic and vibrational degrees of freedom in some sense. But here you just keep excitonic degrees of freedom intact. So you just double vibrational degrees of freedom. But what I'm trying to say is that the meaning of these additional vibrational degrees of freedom is somewhat similar, I guess, to the meaning of the vibrational degrees of freedom in Liouville equation. So if you consider the Liouville as propagation in the bra and propagation in the cat, in some sense you can also assume that you propagate in the bra and the cat different vibrational degrees of freedom. So this is a similarity. I don't know if I answer reasonably your question.
Okay, thank you.
So there's a question from, I'm not sure I'm pronouncing the name correctly.
From Jürgen. Wait a moment.
I think the other one was first, actually.
Oh, right. Okay. Then I will not interfere with you, Thomas.
Okay, so should I go ahead?
Please go ahead.
Okay. Hi. So I have maybe we can stay in the slide to. So I have a question here that you didn't double the system space. And I think this has been discussed, but when the excitonic gap will be very low, so that the finite temperature will create a non-equilibrium population among the excitonic states, which is unlikely in photosynthetic complexes, I agree. But in some other cases, the theory has to be redefined, it seems. So can you comment on that a little bit?
I mean, the theory is based upon, maybe I didn't make it clear, sorry. So yeah. It is assumed that excitonic ground state is totally decoupled from the excitonic excitation. You are absolutely right. I mean, it's not necessary to be the case. I mean, for these systems, yes.
Yeah, and the general thermofield is actually where the system and bath, I think all of the system degrees of freedom will be doubled, right? The Umezawa's work, what is?
Yes. I mean, in principle, you can double all degrees of freedom. But I mean, the idea of our work was just to develop some efficient method, numerically efficient. And of course, if you double all degrees of freedom, then
the same cost as the Liouville equation.
Why do you do that? Why don't you, use Liouville, for example? I mean, we were thinking about that. There are some ways to consider also this situation when the excitonic, when the total number of excitons in all excitonic states in the ground and so on is not conserved. So you have coupling. And you can, it's possible to generalize this method to these situations. But of course, it will require much more efforts and work.
One more question towards that. The bath remains still non-interacting, right? Except the finite temperature part. The bath oscillators will not interact among each other. Am I right in saying that?
Yes. But I mean, but they don't interact with each other in the original from Hamiltonian. In the
but tilde space and the normal space interacts among each other, I guess.
There is no direct interaction. So, so they just interact where proxy, where excitonic degrees of freedom. So if you don't have coupling, if these J's are 0, you just get a bunch of shifted harmonic oscillators. And by the way, in that case, it gives you just alternative way of shifted harmonic oscillator model. So instead of considering these shifted harmonic oscillators at finite temperature, I mean, fully quantum, as people
one can do a Polaron type of transformation and get that.
Exactly. But this is absolutely equivalent.
Yes, different. I have 2 more questions.
But
So
I think maybe we should proceed to if other people have questions.
I see. Okay.
So at least Jürgen had a question. Maybe you can ask questions later.
Yeah, sure.
Jürgen?
Okay, thanks. I'll be quick. Hi, Maxim. Thanks for your talk. So I have a question from the simple mind of an experimentalist. So if I understood your results, then what you're saying is that you predict oscillations in an FMO, a Thermofield fluorescence signal, and these oscillations will be purely vibrational, under these system parameters. Now, can you think of a system where one would look at excitonic oscillations? What would be the parameters, and would your theory be able to capture that also?
But I mean, in principle, your oscillations are excitonic, and so these purely vibrational oscillations, they just come exactly due to the averaging, due to the static disorder. So we in this simple setting, you can just think of static disorder as of ensemble of, for example, FMO mutants, as Greg Scholes, for example, did experiments. So, and every realization of static disorder is just a different mutant of FMO. And for each mutant, of course, you get vibronic dynamics in the excited state. But when you just take all of them and average, so when you do this ensemble averaging over static disorder, only in this case, these vibronic beatings will melt effectively into these vibrational beatings after a certain characteristic time.
So if you did experiments on a single complex, it would be different? Or is that what you're saying?
Yes. So if you, precisely, so if you do experiment on a single complex, you will not see that. So this is just effect of averaging. It's not a dynamical effect in each single FMO, let's say. This is just ensemble effect. This is what you see upon averaging.
Thanks.
I think Donatas had a question.
I have one. Oh,
well, I think Donatas also had, I think he was first.
Ah, sorry, I didn't.
Yeah, actually, I have a question. Actually, more of a comment. But first of all, thanks for the talk and also for the effort trying to explain everything properly. I appreciate it a lot. So the comment is, did you intentionally calculate something that was not measured? Because of course, there are like quite a few pump probe measurements and 2D spectroscopy measurements. So I guess if you wanted to test if your theory works, you probably would have compared it to existing data.
Yes, I mean, there were 2 reasons why we decided to calculate this fluorescence. First, yes, it was a provocative reason. Maybe someone would like to do that. And of course, I mean, from purely theoretical point of view, fluorescence is the cleanest possible signal, so which comes from excited states. It's not contaminated by the ground state bleach and so on.
I agree with that. But do you have plans to calculate? Excuse me. Do you have plans to calculate pump probe or 2D signals?
Yeah. So I'm coming to that. And the second reason was that to calculate pump probe or 2D, we need to calculate excited state absorption. And I mean, it requires a bit more efforts. So at the moment, we just simulated a single excitonic manifold response function. So we can calculate 2D or pump probe without excited state absorber. But work is in progress. I mean, we know how to do that, how to calculate excited state absorber. It just requires more numerically intensive calculations. So, but we plan to do that.
Thanks. And a very quick comment, actually, when we measured, when we did 2D spectroscopy of FMO at 77K, we saw actually pretty strong beatings in excited state because we can
really?
distinguish them. Yeah, there is one strong signal in double cross experiment. And we don't really talk about it very much, but I wonder if your explanation, if your theory provides an explanation for that. I mean, do you think what is, which I must admit I don't understand this very well, with melting of vibronic degrees of freedom, but do you think you will see this effect also in like pump probe or 2D spectroscopy, this type of signals, what you're talking about?
Yes. Absolutely, because I mean, basically, for example, this fluorescence signal is just determined by the stimulated emission contribution to pump probe or to D. So the effect will be absolutely the same.
Okay, thank you.
Thank you.
Okay, maybe quick question from Elisa, and then I think we should proceed after that.
Yeah, thank you. Thank you so much. Yeah, hi, Maxim.
Hi, Eli.
It was a very nice talk, and this idea about this thermofield dynamics. I have a very short question. It's more like a fundamental question, I would say, about how do you model this Hamiltonian in this thermofield dynamics approach. So I was thinking, because this is more like a heat bath situation, right? An interaction with an environment which is a heat bath.
Yes, but this is quite strange heat bath. So you see, it consists of just a bunch of non-interacting oscillators. They just interact due to the fact that you have this excitonic coupling. If you don't have coupling, then you have just independent oscillators in each electronic state. But please continue.
Yeah. So my question is, imagine you have, for example, an interaction with a sort of local environment. So you have your system, which is interacting with another system, which is the bath, but it's not really a bath. So the size is more or less similar to the system. I was thinking, I'm not much into that, but wouldn't these tiled terms that you introduced be like time dependent, or this modeling will be time dependent, right?
But sorry, can you please explain me better why time dependent?
Yeah. So yeah, in this slide, in the last line, you see these terms, which are the time dependent terms, that these style terms. Wouldn't this be?
Eli, sorry, you mean these terms?
Exactly.
But they are not time dependent; they are temperature dependent.
Yes, they are temperature dependent. But if you don't have a finite temperature, so you have like a dynamics that changes in between the system and the bath, wouldn't this be difficult to model? Simply like with temperature, finite temperature.
But I mean, of course, it's not difficult to model from the fundamental point of view. You can just write down your Liouville equation and go ahead. But what we try to do is just to reformulate it to make something which can be used for efficient numerical simulation, because somehow it's much simpler to deal with multi-dimensional Schrödinger equation than with multi-dimensional Liouville equation. And what is also good that when you consider these Schrödinger equation at you see that your initial state is just everything is in the ground state, as it would be for the standard Schrödinger equation at 0 temperature. So this is just a numerical, or I don't know, a trick to make numerical simulations more efficient and simpler. But of course, fundamentally, you can model this temperature by all possible means.
Okay, I think we should, in view of time, proceed. So thank you very much, Maxim.
Thank you very much.
And I will